Hello, everyone. Again, it's your friendly heavy physics teacher. Uh, this time I have a lesson for my Regents Physics class. This is for Unit 11, Lesson 3. Um, and we're going to be talking about what happens when waves encounter a boundary between mediums. Okay, so we call these boundary effects, and they're the effects of reflection, refraction, and diffraction. Okay, and you've all experienced them. You've all dealt with them all your lives. Now we're just going to be putting particular um, uh, properties to these phenomenon, especially as they relate to waves and wave characteristics. All waves do what we're going to be talking about today. Okay. Um, so I may use a particular example of one kind of wave, but it can be applied to any kind of wave that's encountering a boundary, and the boundary has certain qualities that allow waves to pass into them, or maybe they don't pass into them, but they'll bounce off, or maybe some will go in and some will come off. Okay? Now I'm going to use the example of light waves coming from air into window glass. And now this is like a microscopic view of just one particular group of waves coming in. These are the black lines coming in, all right? And they encounter the boundary between the glass. All of that over there is glass, okay? It's just regular glass, but this is what's microscopically going on inside the glass, okay? So the wave's energy is coming in. Now, because there's a boundary, not all of that wave's energy goes through the glass. Yes, a lot of it does, but not all of it. Some of that wave's energy is going to bounce off, all right? Which is why if a person is standing over here, the light waves that have come off of them, that reflected off of them, go to the window, and then a person standing over here, maybe there's a wall right here, but the person standing over here looks into the window, they can see that person standing over here. And that's how this represents reflection, okay? Reflection doesn't just mean you standing in front of a mirror seeing yourself, all right? An echo is a reflection of a sound wave, okay? One of the reasons why boats are told no wakes in enclosed harbors or in narrow places on waterways, especially when those waterways have like concrete sides in a canal or like in a harbor, and they're told no wake or low wake, because when the waves come off of the boat, they'll smash into that boundary between the shore and the water and reflect back into the harbor and create problems. All right. Not only is there the waves coming in from the boat, there's also the waves reflected off. Oh, wait a minute. I got two waves occupying the same point at the same time. Let's hope I'm not at an antинode, because then I get an even bigger bounce because of it. Okay. So we've got two phenomenon happening here. Wave coming in, part of the energy is bouncing. That's called reflection. Part of the wave is going into the new medium. It's getting absorbed by the new medium, in this case, window glass. As it goes into the window glass, changes happen to it. It slows down in this case. And because it slows down, that means the wavelengths get shorter. Okay? That change in speed, that change in wavelength, force the path of the wave to change as it enters the new medium. That change in the path, that change in the speed, creates a phenomenon we call refraction. There is a third phenomenon that isn't necessarily a change from medium to medium, but it's a change in the way the wave can move within the medium. And we call that diffraction. We'll get to that in a couple of minutes. Okay? So, reflection, refraction are what we're talking about now. Reflection. All right? Reflection is when a certain amount of the energy of a wave bounces off back into the original medium off of a boundary in that medium, okay? So you are seeing a reflection of the light bouncing off of the boundary that is this whiteboard in the air, okay? So we've got light coming from off of the walls in the room. We've got light coming from the outside window. We've got light coming from all over. Boom, it's hitting the whiteboard. Most of that light is getting reflected to you. That's the white. A little bit of it isn't. A little bit of it's being absorbed. That's the writing that you see, okay? So we've got light waves coming in, bouncing off of this, but believe it or not all of that light is getting reflected. A lot of it is, but some of it isn't. And overall, the temperature of this board over time would increase a little bit. Okay? That's what we mean by absorption of the energy. But for this example, yeah, you're seeing a whole bunch of reflection happening here. Okay? Now, if this were a mirror, it would be nice and smooth and you'd see an image and it would look like it'd be going back and forth and back and forth and back, one of those infinite thingamajiggers. Those are pretty cool. All right. If this were at an angle like this, okay, and you could see an image, boink, boink, the angle that it makes with the surface, okay, is not the angle of incidence. You have to draw a normal line. In other words, a perpendicular line to the boundary. That's where you make your measurement for angle of incidence. That's where you make your measurement for angle of reflection. You don't make it with the surface. In all cases, the angle of incidence, the angle that it comes into the boundary at, is equal to the angle of reflection, the angle it bounces off the boundary at. Okay? All right. Refraction. Refraction happens when some of the wave's energy, or all of it, passes into the new medium. Okay? Refraction happens because the path of the wave bends, causing a change in speed, causing a change in wavelength. That forces the change in the direction of the path. Okay? So, refraction is caused by the fact that it's going to change speed in the new medium, it's going to change wavelength in the new medium. The thing that does not change as it crosses the boundary is the frequency. And I can't emphasize that enough. Okay? So, if we were to shine a light into water, and it's a laser light, you put a red laser light into the water, it doesn't change color when it enters the water. It's still red. And that's all based on the frequency. Okay? You shine a green light through the light or through water, and the water stays green, or I should say the light in the water stays green. It doesn't change color because it changed path. It doesn't change color because it changed speed. The frequency stayed the same. Same thing with sound waves. Sound waves that go from the air into water, you would hear them the same pitch. The pitch doesn't change. The frequency of the sound doesn't change. It may go faster once it goes in the water. It'll have a longer wavelength when it goes in the water, but it'll be the same frequency. All right. So a siren you might hear above the water, in the water, would also sound like the same siren. Okay. Now, the property of a medium that determines the speed at which the wave will pass into the new medium. The property is known as permittivity. Okay. Now, for you Regents folks, the textbook that I had to use refers to density, but they don't mean physical density. They're using the term density in the textbook to talk about the slowing effect that the medium would have on a wave moving into it. It's totally the wrong way to use density. I've always hated that one aspect of that particular textbook. All right. And part of the reason is I think they thought permittivity would be confusing. I really don't understand that decision for them. Okay. And now that I'm making this public, I'll probably get called into question about it. But permittivity is the term that we use to represent how much a material affects the motion of the wave through that material. Okay, a high permittivity material means that a particular wave will have a high speed through that material. A low permittivity material or a low permittivity medium means that the speed of the same wave will be lower than in a different material with a higher permittivity. Okay, so this has particular application for our refraction. Okay, if we go from a material, this is material A up here, and it has a high permittivity to whatever this wave is. Okay, and this represents the path of the wave. Imagine there's a whole bunch of cross lines, parallel lines coming down this perpendicular to this path. Okay, so we have this wave coming in here, all right, and it's going from a high permittivity medium to a low permittivity medium. This would be a light wave moving from, say, air into glass or air into water. All right. Air has a high permittivity to light. Water has a lower permittivity to light, not necessarily low permittivity, just lower permittivity. And because of that, it's going to change this angle. The angle of incidence up here, theta A. The angle of refraction down here, theta B. The speed in A is going to be higher than the speed in B. The wavelength in A is going to be longer. They will be more spread out up here in A than it will be down here in B. And so because of this change in speed, because of that change in wavelength, the path has to bend. The path has to bend. The greater the difference in permittivities, the more bending that occurs. Notice where I'm measuring my angles from. Normal line to the boundary between the mediums. Okay? You always measure your angle from the normal line to the boundary between the mediums. Over here, we reverse that. We're going from, excuse me. This should say low permittivity, high permittivity. Wow. Let me change that. Okay, I got it changed now. Okay, so we're going from a low permittivity medium into a high permittivity medium. Okay, an example of this might be sound going from air into water. All right, the sound wave coming from the air, encountering the boundary with the water, that will change the path of the sound wave in the water. Okay. Interestingly enough, sound moves faster in water than it does in air. Okay. So the wavelength over here in the water is going to be lower than the wavelength over here in air. The speed of the wave in air is going to be lower than the speed of the wave in the water. All right. That causes a bending away from the normal line. That causes an increase in the angle between the angle of incidence and the angle of refraction. All right. So that's why theta B down here is bigger than theta A. And all of that is dependent on how big the speed change is between the two mediums. And all of that is dependent on the difference in the permittivity between one medium and the next medium. Okay? Finally, we have a boundary effect we call diffraction. And this is a boundary effect not between mediums, but it has to do with the fact that we have some sort of hard barrier in a particular medium, and we might have a hole in that barrier, or we might have an edge to the barrier and then it opens out. Okay? And in either case, we get a bending of the wavefront to try and fill the empty region beyond that barrier. All right? Energy does not like to stay only traveling in one line. All right? It likes to spread out and fill any region it's moving into. So over there, we have a wave coming into this barrier that has a hole in it. That could be a pinhole in a piece of cardboard. That could be the opening in a seawall for a harbor. That could be your ear canal. All right, sort of thing. And so the wave coming into that is going to bend to fill the region, the empty region beyond the barrier. Over here, we have this edge that the wave is traveling along, and then it reaches the end of that wave. Well, that's going to cause a bending of the wave around it into this empty part over here. Yep, not all of it gets filled. This would be a shadow part. Over here and over here, these would be shadow parts for the phenomenon that's happening. All right. But someone standing down over here wouldn't be able to see the source of the waves, but they would be experiencing the waves because they bend and get over to that person. Someone standing over here might not see these light waves coming through, or might not hear the sound waves that are coming through the hole in the wall. But someone standing over here, while they're not in direct line with the waves that are being made, they are in a line of the bent waves that are produced as the waves attempt to fill the region. Okay? So diffraction, bending of a wave front, not the path of the wave front itself, the whole wave is now bending. So the boundary effect phenomenon are the boundary effect phenomenon are reflection, when the wave bounces off the boundary. Refraction, when the wave passes across the boundary, when it goes across the boundary and there's a change in speed, and you get that bending effect because the change in speed causes a change in wavelength. The change in wavelength forces the path of the wave to bend. Okay? Refraction, no change in frequency. Diffraction, waves want to go out and fill any empty region they're moving into. That's the point of energy. It wants to spread out and fill as much of a region as possible. That's why the farther you get from a wave source, the dimmer it appears if it's light, the softer it sounds if it's sound, and because that energy is spreading out to fill the space into which it's going. Okay, so all of these three effects, reflection, refraction, diffraction, happen because there's some interaction with a wave, between a wave and either a change in medium, or we've got a change in the pathway that can happen within the medium. All righty. Thank you very much for your attention, and I'll see you online soon. Have a great day. Let's stay safe in this time of uncertainty. This is your friendly heavy physics teacher signing off once more. Have a great one.